So here in this lecture, we are going to discuss Jacobi's method. So consider the differential equation of this form: f of x, y, z, ux, uy, uz is equal to 0, where x, y, and z are independent variable and u is a dependent variable, depends on x, y, and z. And this differential equation does not involve or it not appearing u function. If you want to say that a solution for this differential equation is of this form: a capital F of x, y, z, a, b, c, there are three arbitrary parameters are there. If you want to say that this is a complete integral, or I can say complete solution for this differential equation, if this is of rank 3. Is the same manner we have a differential equation x, y, zx, zy, and z equal to 0. And if I want to say that capital F of x, y, a, b is the solution of this differential equation if fx, fa, fxa, fay, fb, fbx, and fby is of rank 2. Same manner, this idea we can extend for this matrix, which has a rank 3. Then we can say that this solution u is equal to f of x, y, z, a, b, c is a complete solution or complete integral. Now let us discuss the Jacobi's method here. That means if I consider this f of x, y, z, ux, uy, uz is a differential equation of this type, and consider a two parameter family, that is h1 is this a one parameter family is x, y, z, ux, uy, uz, a equal to 0, and h2 is this family. If I call this as the equation number 1, I can say this is equation 2, this is equation 3, such that, so these two equations I'm considering with this condition, that is a Jacobian of f h1 h2 with respect to ux, uy, uz is not equal to 0. And the Pfaffian equation that is du is equal to ux dx, uy dy plus uz dz is integrable. So this Pfaffian equation is integrable, where there's the value of ux, it is in terms of x, y, z, a, b. uy, it is also in terms of x, y, z, a, b. And uz is also obtained solving or obtained by solving equation number, we have 1, 2, and 3. So if you can solve this three equations, solving equations 1, 2, and 3 by virtue of, if I can say this is equation 4, then we have this. And such h1 and h2 are such h1 equal to 0 and h2 equal to 0 are said to be compatible. Compatible with f equal to 0. Observe that this equation 4 which we have here is either an exact equation or it is not integrable at all. The equation 4, that is a Pfaffen equation we are talking about, is exact equation or not integrable, or the solution for that one is not possible. Now consider the condition where this equation 4 is exact. So the condition for the equation number 4 to be exact are del ux upon del y is equal to del uy upon del x. So these two quantities are same. Del u y upon del z is equal to del u z upon del y, del u z upon del x is equal to del u x upon del z. If I can call this as equation number 5. So this is the condition is for that the equation 4 that we have here, this equation is to be exact. And this equation 5, so this equation 4 is gives a complete integral of our equation. That means the integral of equation 4 gives complete integral of f of x, y, z, ux, uy, uz equal to 0. So whatever the solution or whatever the complete integral of that one will give given by this. Now, what will be the condition that this h1 equal to 0, h2 equal to 0 are compatible with f equal to 0? So for that we have this theorem, which tells you that if h1 equal to 0 and h2 equal to 0 are compatible with f equal to 0, then h1 and h2 satisfies this condition, that is del f h upon del x u. That means the Jacobian of f h with respect to x ux plus del f h upon del y uy plus del f h upon del z uz equal to 0. So this is the condition where this h is equal to, you can just substitute h1 and h2 both. So where h is equal to hi, where I is running from 1 and 2. So this is the condition for compatibility of this h1 and h2 are compatible with f equal to 0. And if it is compatible, then according to this theory, we'll able to find out what is the solution for this Pfaffen equation. Let us try to prove this statement. So proof of this. So we have here differential equation, that is fx, fxyz, ux, uy and uz equal to 0 is the differential equation we have. On differentiating, with respect to x, y, and z, we get. So what is the situation? Here is your function f, which is a function of x, y, z. There are 6 variables are there: x, y, z, ux, uy, and uz. And this ux, ui, uz are the functions of x, y, z. All these 3. So if you want to differentiate with respect to x, there are 4 paths you can go through. One is this, another one is here. For ux, you have three variable x, y, z, and for uz, you have x, y, z. So that the 2 things is here. So that's why it is del f upon del x plus del f upon del ux uxx plus del f upon del uy uyx plus del f upon del uz uzx equal to 0. This is with respect to x we have. Similarly, with respect to y and with respect to z we can get. So del f upon del y plus del f upon ux uxy plus del f upon del y uyy plus del f upon del uz uzy equal to 0. The last one is del f upon del z plus del f upon del ux uxz plus del f upon del uy uyz plus del f upon del uz uzz equal to 0. Now similarly, we'll do the same thing which we have did here for f. We'll do for this h. H is h1 and h2. We'll do for that both. So now consider h1 parameter family, that is h of xyz ux uy and uz equal to 0. If you consider this as one function where h is nothing but the hi, I is running from 1 and 2. So that means I'm taking whatever they're doing for h, it is for h1 as well as h2. On differentiating, with respect to x, y, and z, we obtain del h by del x plus del h by del ux uxx plus del h by del uy uyx plus del h by del uz uzx is equal to 0. Same thing which with y also we can write. And same thing we can write for z also. So this is the things we got. Now I'm call these equations which we have here as the equation number 4 we can get. So let's say this is 5 also I should I think so. Yeah. Pi is also denoted. So this is sixth equation, seventh equation, eighth equation. This is ninth equation, 10th equation, and 11th equation. And you just note that this 9, 10, and 11 is also true for H1 and H2, both. So ultimately, it is 6 equation altogether. Now what we'll do, we'll multiply this equation number 6 by del H by del X. And equation number 9 by del F by del Ux. And then subtract both of them. So what I'll do is the sixth equation is multiply with del H by del Ux. And this one is subtract with the equation number 9 is multiply with del F by del Ux. So what will happen with this one, if I can do this one, that is del Hu by del X. So this equation is del Hu by del X is multiply. So this quantity, this term will be cancelled out in the both when you subtract this two. We get del F upon del X into del H upon del Ux. You just have the first term here. When you multiply by del H by del Ux. Here you will have del F by del Ux into del H by del Ux Uxx. That cancel with here, that this term. And this term is already there, that is minus del H by del X into del F by del Ux. Plus the term having Uxy is there. And plus term having Uxz is there. The term having xxx is cancelled out. So we'll have del F upon del Uy into del H upon del Ux minus del F upon del Ux into del H upon del Uy. Here you will have del F upon del Uz into del H upon del Ux minus del F upon del Ux into del H upon del Uz. Okay, and these things we can got since Uxy is same as Uyx, Uyz is same as Uzx, and Uxz is same as Uzx, which we have already used here. Now once you have did this one with 6 and 9, now the same things you can do for 7 and 10 and 8 and 11. To do that one, we need to remove this YY term, and here from this ZZ term, UZZ, UYY, that term we need to cancel out. So for that, what I will do is the equation number 7 is multiply by del H by del Uy and subtract from equation number 10 with del F upon del Uy. We obtain, if you do this one, we'll obtain del F upon del Y into del H upon del Uy minus del F upon del Uy into del H upon del Y plus the term having Uxy plus term having Uzzy, Yz. What you will have with the term xy, you will have del f upon del ux into del h upon del uy minus del f upon del ui into del h upon del ux. Here you will have del f upon del uz, del h upon del uy minus del f upon del uy into del h upon del uz. And the last one, that is the equation number 8, is multiply with del h upon del uz subtracted from equation number 11 that we have here, del f upon del uz. We obtain, that means the term having u z is cancel out. What will we get? It is del f upon del del f upon del z into del h upon uz minus del f upon del uz into del h upon del z. This is the first term. Now the term having u x z, that is del f upon del ux del h upon del uz minus del f upon del uz into del h upon del ux plus a term having yz. So you'll have del f upon del uy, del f upon del h upon del uz minus del f upon del uz into del h upon del uy. And if you add now this equations, that means if I can say this is the equation number, what was the last equation was 11. Now if I can say this is the 12th equation, this will be the 13th one, and this will be the 14th one. If I add this, so adding 12, 13 and 14, we have our required equation. That means we'll have del f del h upon, so in the first equation that you will have, you can just observe what will be the first discrete quantity. This quantity is del f h upon del x ux. This quantity will be cancelled out. You just observe this two quantity uxy and uxz. Uxy is here, so that will cancel out with some quantity from here. So what we can have, just only left quantity is del f h upon del x ux plus del f h upon del y uy. That is the quantity from equation number 13 is left. This quantity is cancelled out, this two. Similarly, in the 14th one, this quantity is left, this two quantity will be cancelled out. So plus del f upon del h upon del z uz equal to 0, and which is the required result that we are looking for, required result. And this equation can be rewritten. So you can just observe that this is true for h1 and h2 both. Okay, and this equation, that means the last equation which we have, the above equation can also written as, that you just observe that what is del f. So as per this, it is del h by del x. The coefficient is f ux. So in that manner, I can write down it is f ux del h upon del x plus fuy del h upon del y plus fuz del h upon del z minus fx del h upon del ux minus fy del h upon del uy minus fz del h upon del uz equal to 0, which is a semi-linear PDE for H. This is the semi-linear equation, PDE for H. And that is given F is H1 and H2 satisfies this equation. That means this equation, let me write that. So that is for given F if H1 and H2 satisfies the equation gradient of F H1 H2 upon Ux Uy uz is not equal to 0 and the previous equations double star or star and the equation double star, then H1 equal to 0 and H2 equal to 0 are compatible with F equal to 0. And we'll have one example which correlate with this one. Okay, so let us see this example. Using Jacobi's method, solve equation that is a z square plus z ux minus ux square minus uy square equal to 0. So first of all, you just observe that this equation is of the form f of x, y, z, ux, uy, and uz equal to 0. This is of this form. So as per our situation, what will be the equation number double star? We can write. That is for H1 and H2 both. Okay. So the equation double star, the equation for H1 and H2 is, let me write that ux del h del x plus fuy del h by del y plus fuz del h by del z minus fx del h by del ux minus fy del h by del uy minus fz del h by del uz equal to 0. So what is, this is my function f. It is the variable as x, y, z, ux, uy, uz. They are the variable. So what is the partial derivative of this with respect to ux? Will gives me z. So it is z del h by del x. This is not d, it is del. That is the first equation we can have. Sorry, this is, I have written wrong. This is z is here. This is uz. So the partial derivative of this with respect to ux is actually minus 2ux. Partial derivative of this with respect to y will give you minus u 2uy del h upon del y. The partial derivative of z with respect, partial derivative of uz with respect, or uz is z. So that's why it is z del h upon del z minus fx will be 0 into del h upon del ux. Fy it is also 0, 0 into del h upon del uy minus fx, that is 2z plus uz. So that is 2z plus uz del h by del uz equal to 0. Now this is, what is this? It is a linear equation in terms of h. So what are the auxiliary equations are? So therefore the auxiliary equation are d by or dx upon whatever the quantity you will have here, that is minus 2ux, minus 2ux is equal to dy upon minus 2uy that we have here. Then it is equal to dz upon z ux upon 0 del uy upon 0 due to the this quantity 0 0, and this one is last one is equal to u du z is minus 2z minus uz. Now how to solve two linearly independent solution of this auxiliary equations, or from this system we'll have two solutions. The first one have dux upon 0, so that will gives me, this will gives me dux is 0 and duy is 0. So that will gives me ux is constant, let's say a, and this will gives me uy is constant, let's say b. And what is our objective is actually calculating the value of ux, uy and uz in terms of x, y, z and ab. So this is ux, uy, and now we need to calculate the value of uz using this given equation. So here, given that is a z square plus z into uz minus ux square minus uy square equal to 0. If I substitute the value of ux and uy, that will give me z square plus z uz minus a square minus b square equal to 0. So that will give me uz will be a square plus b square minus z square upon z. So we'll have now the value of u, it is in terms of a, value of uy which is in terms of b, and uz in terms of x, y, z and ab. So now the Pfaffian equation, that is have ux dx plus uy dy plus uz dz equal to 0. We have to solve this one, and we need to have this is equal to du. We need to have this is a exact differential equation. So du equal to a dx plus b dy, because that is the value of ux, this is the value of uy, and the value of uz we have calculated this a square plus b square minus z square upon z dz. And if you integrate both sides now, to integrate one, no problem with this one. Second one is also here we have need to do some arrangement. So that is a dx plus b dy. This I can write down a square plus b square into dz by z minus z dz. So we'll divide this in this manner. This is equal to du. So therefore, if I take the integrate both sides, so on integrating, we obtain u equal to ax plus by plus a square plus b square ln of z minus z square by 2 plus some another constant c. If you want to check that whether this solution which we got, it is a complete solution, then you have to check that this matrix that we have here is of rank 3, and we already compute that it is of rank 3, and our theory says that it is a complete solution. So that's why this is a complete solution for the given differential equation. So which is a complete integral for given PDE. Let us solve one more example. So that a complete integral of the function f of ux u is equal to 0 is u equal to ax plus by plus cz plus d, where f of abc is 0, and hence find the complete integral of ux plus ui plus uz minus uxy ux ui uz equal to 0. So here I just directly write down now the auxiliary equation for the Jacobi's method. So as per the discussion, the Jacobi's method, the auxiliary equations are this: dx upon fux, dy upon fuy, dz upon fuz, dux is upon minus fx, duy upon minus fy, and duz upon minus fz. So that is our auxiliary equation for this Jacobi method. Will tell you that dx upon fux is equal to dy upon fuy is equal to dz upon fuz equal to dux upon minus fx, duy upon minus fy, duz is equal to minus fz. So that will gives me dx upon fux. So I'll just, we don't know what is the function, so it will write as it is. This is dy upon fuy, dz upon fuz as it is. Dux upon, since this function does not contain x, y, and z, so the derivative of fx is 0, fy is 0, fz is 0. So that's why this will gives me 0 equal to du y upon 0, duz upon 0. So hence we can have ux is some constant, let's say a, uy we can take as b, and uz as a take c. And if you can have this, then the Pfaffian equation, that is du equal to ux dx plus uy dy plus uz dz will gives you du equal to a dx plus by b dy plus c dz. So if I can integrate this one, then you will have u equal to ax plus by plus cz plus some constant d, where a, b, c and d are the constant, and all this a, b, c, d are satisfies the equation is the given equation f of this ux is given as a, ui is b, and uz is c. So that's why that's satisfy this equation. So I should write where a, b, c and d are constants and they satisfies the equation f of abc equal to 0. And this completes the solution for this problem. Now the next problem is find the integral of this one. So as per this argument, now here this is a function of fx, fy, fz. So the solution for or the complete integral for the given the complete integral of that equation, that is ux plus uy plus uz minus ux uy uz equal to 0 is a plus b plus c minus abc equal to 0. So that is the solution, where you can write down it is in tops of C if you want. So that is the things we got. Now, so this is regarding the Jacobi's method that we have. Now the next things that we can have, it is we need to find out the solution of this equation, that is fx is equal to x, y, z, pq equal to 0. We already discussed to solve the complete integral of such type using the Shanti-Peace method. Now the question is, can we able to solve such type of differential equation using Jacobi's method? That means finding the complete integral of first order PDE in two independent variables. So these are the two independent variables are here. And we know that the value of P is del Z by del X and the value of Q is del Z by del Y. So to do this one, let us consider this equation. Consider the PDE this of this form. Now the solution of, if I can say this is the equation number 1, the solution of 1 is the relation between x, y and z. If this relation is u of x, y, z equal to constant, then now this P I can write down. We know that the value of P is del Z by del X. So it is del U by del X upon del U by del Z. So that is nothing but the minus UX upon UZ. So that is the things we can use here. And Q we can write down, it is minus del U by del Y upon del U by del Z. So that is equal to minus uy upon uz. Now, if you substitute this value of P and Q in this equation 1, then this equation 1 can change into the 3 variables, that is ux, uy, uz, xyz. On substituting, the above values of p and q in one, we get some function g which is in terms of x, y, z, ux, uy, and uz equal to 0, which is in the form given in our original equation f of x, y, z, ux, uy, uz equal to 0, and can be solved by Jacobi's method, as we have discussed earlier. So let us solve such one example based on this. So find the complete integral of the equation p square x plus q square y equal to z by Jacobi's method. So let us try to solve this. So we know that p value of p is minus, as we have discussed earlier, that is the value of p is minus ux upon uz, value of q is minus uy upon uz. So we'll say substitute this value into this equation. P, we know that the value of p is minus ux upon uz and q equal to minus uy upon uz. Putting this value in equation 1, we get p square, that is the square of this one, ux square upon u z square into x plus u y square upon u z square into y is equal to z. If I multiply by u z square both sides, then this equation will change to, you just observe that it is x ux square plus y uy square equal to, that is z uz square. So the auxiliary equations are for the Jacobi's method, that is dx upon f ux, dy upon f uy, dz upon f uz equal to dx upon minus fx, dy upon minus fy, dz upon minus fz. This is the auxiliary equation for Jacobi's method. And this is my function f. So that is dx upon fx. So that will gives me 2x ux is equal to dy upon 2y uy is equal to dz upon minus 2z uz, because if I can take this is on the other side, that is fx or dx upon fx is ux square, so it is minus ux square, fy upon u minus uy square, and this is minus minus become plus uz square. Now solving this, we need to consider a two solution for this. So it is up to you how we can obtain. So you'll just compare this one and this one, and this one and this one. We'll get two solutions for this. In terms, so I need to calculate what will be the ux, uy, and uz in terms of x, y, z, a, and b. There are two constant a, b is there. So this will gives me now dx upon 2x ux is equal to dux upon, sorry, this is not, this is ux, uy, uz, ux, uy, uz is here. I forgot, huh? U. So that is dux upon minus ux square. Ux square. One ux is cancelled out. So that will gives me dx upon x is equal to minus 1 upon, sorry, 2 into ux dux. If I take the integration, that will gives me ln of x is equal to minus 2 times ln of ux plus some constant ln of a. So we can write down this one, it is x into ux square equal to a. Similarly, we have dy upon, here it is 2y dy is equal to duy upon minus uy square. One uy is cancelled out. So this will gives me dy upon y is equal to minus u dy upon uy, and 2 is there. So that's why it is ln of y is equal to minus 2 ln of uy plus some ln of b. B is a constant. So you will have y into uy square is equal to b. So that means this will gives me the value of ux is a upon x raised to 1 by 2. And uy will have b upon y raised to 1 by 2. And from the given equation, that is this, the value of uz we can also obtain. Given that, or we have, what we have, it is x ux square plus y uy square is equal to z uz square. So it is x ux square we have already obtained, that is a by x, plus y into b by y is equal to z uz square. X will get cancelled out, y is get cancelled, so you will have uz square is a plus b by z. So that will imply uz is a plus b by z whole raised to 1 by 2. So now the Pfaffian equation, that is u du is equal to ux dx plus uy dy plus uz dz. The value of ux we have obtained it, that is a upon x raised to 1 by 2 dx. The value of y is b upon y raised to 1 by 2 dy. Plus this is a plus b by z raised to 1 by 2 dz. And if I take the integration both sides, we'll have u equal to the integration of x raised to 1 by 2. It is minus 1 by 2 is there, so that's why it is plus 1. So it is gives me ax raised to 1 by 2 into 2 plus by raised to 1 by 2 into 2 plus a plus b into z raised to 1 by 2 into 2 plus some constant c. So this is the value of u we'll have. By writing, the ultimate goal is to obtain the value of this differential equation. That means we need to calculate what is z in terms of, ultimately our objective is not finding u, our objective is to finding the z, because this is a two parameter or two independent variables are involved here. What we got here, it is z, sorry, what we got here, it is u. So by writing u equal to some constant c, so here we'll have c, that c will get cancelled out. Okay, and if I can read, so we get the complete integral of the given PDE as How we got that is 2 into ax raised to 1 by 2 plus 2 into bx raised to 1 by 2 plus 2 into a plus b x z raised to 1 by 2 equal to 0. So this 2 will get cancelled out. So we'll have ab plus a plus b z raised to 1 by 2 is equal to minus of ax raised to 1 by 2 minus of bx raised to 1 by 2. If I take square both sides and divide by a plus b, so that will gives me ax plus b upon a plus b raised to 1 by 2 plus bx upon a plus b raised to 1 by 2 and whole square is there, and that is equal to on this side it is z. So the value of z we got, it is this, which is the complete integral of the given differential equation. Let me solve one more example. Let me have this p square plus q square y is equal to qz. The question is to obtain the complete integral of this differential equation. So we have to put z is equal to here minus, sorry, not z, t equal to minus ux upon uz and q equal to minus uy upon uz. Substitute here. We'll have it is ux square upon uz square plus uy square upon uz square whole into y is equal to q, that is minus uy upon uz into z. If I multiply by uz both sides, we'll have ux square plus uy square into y equal to minus uy into uz into z. So the auxiliary equation R. I will write directly what are the auxiliary equation, that is dx upon f ux. You just observe that f ux is 2 ux into y, that is 2 ux into y is equal to dy, it is fy. So we'll have 2 uy into y, and this quantity goes on the other side, that is uz plus z. So plus uz into z is equal to uz upon, that is uy z ux upon fx. X is not involved here, so that's why this is 0, equal to uy upon fy, that is this, that is ux square plus uy square equal to uz upon, this is minus, upon the derivative of this with respect to z. If I take this on the other side, that is ux into uy into uz, and which is of minus sign. So this is the first thing which we got from here. It is ux is constant. So ux is constant because dux upon 0 is there. So a is constant here. Now we need to calculate another solution for this one. So you can apply anything. Let me compare this one and this one, because it's on involve only this ui will get cancelled out, and you will it always only involve ux and z. So we'll have dz upon uyz equal to duz upon minus uy uz. Ui is cancelled out. So you will have dz upon z plus duz upon uz equal to 0. So take the LCM, ln z plus ln uz equal to constant 0. or constant, let's say ln b. So that will gives me z into uz is equal to constant b. So that will gives me uz is b by z. We already have ux value is constant a. Now the objective is to calculate the value of ui. We have this equation. We have the value of ux, uz. Substitute here, we will get the value of ui. Now we'll have this, that is u square, ux square plus uy square into y, ux square plus uy square into y equal to, we'll have minus ui uz z minus ui uz into z. Now ux, the value of ux is a, so it is a square plus uy square into y. So this is minus ui uz, uz is b by z into z. This z is cancelled out. So that will gives me u a square plus uy square into y equal to minus ui into b. That is a square y plus uy square y plus uyb equal to 0. This is a quadratic equation in terms of u, y, uy. So you can have one solution for that, u square into y, that is ax square plus bx plus c equal to 0. This type of equation is this, plus uyb plus a square y. So this is the value of c, this is the b is b here. Instead of a we have y. So the ui is minus b plus or minus b square, that is b square minus 4. A is y, c is this a square y upon 2a. A is y. So finally we'll have what we have, it is minus b plus or minus b square minus 4 a square y square upon 2y. So now the Pfaffian equation, that is du equal to ux dx plus uy dy plus uz dz, u equal to, or du equal to, we have this value is ux, we already have a. So it is a dx plus this, that is I can say minus b by 2y dy plus or minus under root of b square minus 4a square y upon 2y dy plus uz. uz is a by z, uz is b by z, that is b by z dz. If I take the integration, we'll have this u equal to, this is ax plus this will gives me minus or plus minus b into ln y 2 times 1 upon 2 is there, yeah, plus or minus here you can integrate this one. This is by taking some quantity, some variable. So I'll just take that one as integration under root of b square minus 4a square y square upon y 2y dy plus b ln of z plus some constant c. Putting u equal to c, this u will get cancelled out and you will have z is equal to some function in terms of xy you will have here. and that is your complete integral of this differential equation, given differential equation. That is a Jacobi's method is there. So that's it for Jacobi's method. If you have any question, you can ask.